Okay, can you see this red dot moving around?
Yeah, we can see both the end of your cursor.
Yeah, okay, okay, good. Yeah, then that should be fine. I'm going to share other things in the middle. So and also I have my laptop, sorry, my iPad is also connected in case there are questions and I can write something. Maybe can we just try this if okay, then I have to unshare it. Well, okay, when it comes to actually, I mean, I can write something on my iPad. So if people have questions, I will share the iPad, but I think that should work.
No problem.
Yeah.
Okay, great. So we're happy to welcome Joanna Kmenger as the third lecturer of the school. So Joanna is a physicist working on string theory and quantum field theory with a particular interest in gauge gravity duality and its application, and she's the author, one of the authors of the famous book on gauge gravity dualities that is maybe the standard textbook in the field. So she's going to give us 4 lectures as an introduction to the physics of gauge gravity dualities aimed at philosophers, so that we can finally know what we are actually talking about instead of just talking our mouths. And as usual, the format is just 2 hours of lecture, and you're welcome actually to ask as many questions as you feel like during the lecture, so that Joanna can gauge how to proceed with the lectures, if they need to be slower or she can go faster. So please ask as many questions as you see fit, and don't hesitate to just interrupt and ask. Okay, I think I've said everything. So Joanna, please, the floor is yours.
Yes, thank you very much. So thanks very much for the invitation. As I said, I'm really sorry that I can't be there. I really was looking forward to traveling to Urbino, which I think is a lovely place, and it's very famous for philosophy, in particular philosophy of science. But unfortunately, I broke my arm. So last week, just the day before last Sunday, and okay, so I'm a bit stuck here. But fortunately, I broke my right hand, but I'm left-handed, so if there's questions, I can write on my iPad, so that's already good. Okay, so the next important remark is that I'm a physicist. Okay, so I'm a real physicist, and for me, it's extremely hard to judge what the level of my lecture should be, because of course I would like you to learn something, but I don't want to go into too many complicated details, but also on the other hand, I don't want to tell you things that you already know. So please, I need a lot of feedback from your side. Just ask as many questions as you like, and I'm very flexible to answer the question. I think it's much more important to really have engage in some dialogue, and I don't have to reach any particular goal. I just want you to learn as much about gauge gravity duality as we can. Okay, so let me get started, and really please interrupt me at any time, and I can go into more details if you like, and also I can skip things if you already know them. Okay, so that said, so I'm a physicist, but so this is a lecture introducing gauge gravity duality to philosophers. So okay, now I can't. Yeah. Okay. So maybe let me make a few general remarks at the beginning. So okay, I'm going to talk for 1 hour, and then I think we should have a 5-minute break, and then I continue for another hour before we have the longer break. I don't know if you know where Würzburg is, because it's a rather small town in the north of Bavaria, or rather a part of Germany called Franconia, which is a part of Bavaria. And I'm sure it's not quite as beautiful as Urbino, but it's not too bad. There's a river called Main, which is the same as in Francoforte, Sulmino, okay. And here there's a famous Baroque castle of the Prince Bishop who used to be here. And he invited the famous Italian painter Tiepolo to draw a fresco in the staircase. And that's a UNESCO World Heritage painting. So I'm sure there's lots of paintings by Tiepolo in Italy, but if you want to see a very beautiful one, it's actually here. Würzburg is a strange German name, but there's a Latin Greek version which is called Herbipolis, which is a good translation of Würzburg. Okay. And so now just to tell you where this is, so Würzburg is there. And you see that there's Munich here and there's Frankfurt there. And we are on the same river as Frankfurt. So it's actually closer to Frankfurt than Munich, which is our capital. Okay, and as a last piece of information, so this is our group working on gauge gravity duality. Here you can see me. And so there's really many people here in Würzburg involved in this kind of research. And just to introduce them to you. And so, of course, a lot of the work is also done by my collaborators, and I should be grateful to them. Okay, all right, so let's start with the physics. And so the aim of these lectures that I'm going to give to you is to explain to you what gauge gravity duality is, because the duality in particular is this word which is in the title of the conference or school. And so to start, I mean, physicists tend to be extremely brief, and I think you want to learn a lot of detail about the concepts and so on. So, but let me just start with this very brief slide. So I would just say for now that duality is a map, but okay, one purpose of this lecture is to explain in a lot more detail what this map actually does, okay? And it's a map between a quantum field theory in flat space, which does not have gravity, and this quantum field theory in flat space is mapped to a gravity theory. So you have a map in the mathematical sense between a quantum theory which has no gravity and on the one hand side and a gravity theory on the other side. And that, of course, I expect is also very interesting to philosophers of science because it teaches us new things about the nature of quantum theory, of course. Okay, so I should say that this is a new area of research which followed this very seminal paper by Malacena on the ADS-CFT correspondence in 1997. And okay, so that's certainly a paper that changed the life of many. So at the time, when this paper appeared, I was a postdoc. And so one morning I looked at the archive and there was this paper and I said, oh, this sounds interesting. But I was very young and, you know, I didn't have a lot of oversight, but already then I could actually see right away that this was a super interesting paper. And certainly, I mean, certainly my career also depended quite a bit on this proposal here. Okay, so the point of this lecture is to explain what the duality is to physicists, or what this particular duality is to physicists. And apart from explaining the basic concept of this duality, I would also like to show you some ideas of finding further examples of the gauge gravity duality in addition to the original ADS-CFT correspondence. One other question that is interesting to physicists is to find criteria for QFTs to possess a gravity dual. And certainly one very big question is the following, that the original example of this duality, which is the ADS-CFT correspondence, arises from string theory. And so now a big question is if this duality is actually valid more generally than beyond string theory. Okay, so and maybe you are interested to learn that I changed my mind on this. I mean, a long time I just thought that this is very closely tied to string theory, but more recently I've thought maybe that's actually not true, and this idea can be valid more generally. But certainly the best understood example is still the one which comes in the context of string theory. Okay, and so as I will tell you, gauge gravity duality on one hand side has very fundamental aspects, but it has also these new applied aspects. And in the sense, this was first a spin-off, but I think now it became also a bit of field on its own, is the idea to calculate observables in strongly coupled quantum field theories from this gravity dual. And I want to explain this also a little bit. So I'm going to talk both about the fundamental aspects and also the applied aspects of this duality. And well, I mean, one obvious thing I have to say at the beginning, and this will appear all the time throughout the lectures, is that so far there's no mathematical proof of this gauge gravity duality. I mean, there's other examples of dualities in physics where actually a proof is possible, but in this case, it's not. And I will explain why it's so hard to prove this duality. So somebody would like to ask a question, I think.
May I ask a very elementary question? Yeah, thanks. So, you know, I've often heard, as you say, that this original example arises from string theory, but as you say, the map is between quantum field theory in phase space, in flat space, and gravity. So is the gravity the string theory? So I'm just like, where is the string in that, the way you said it initially?
Okay, that's an excellent question. I would spend almost the entire lecture today to explain exactly what I mean by this sentence, okay? But it's a very good question. So I will explain this in great detail today, okay? But let me just give you a flavor of the answer for now, which is by no means exhaustive. But what you are asking is exactly what I want to convey to you, okay? So
no, I was just asking where the strings come in here, because you
said, yeah, exactly.
Yeah.
I will tell you where the strings come in, and the point is that this duality actually is a particular low energy limit of string theory. Okay, so in principle, so you start with these extended objects, which are strings, and then you take a low energy limit, which means the resolution becomes very bad, or you go very far away from these strings, and then you only see them as being points again. Okay, and then it's the low energy limit means you make the resolution of your microscope bad, or on the other hand, you just go very far away from your strings, and then they look like points, although they're not. Okay, so and I will show you that. And that's just precisely where this word duality comes in. Okay, so wait, be a little patient for me, more details, because this is exactly what I want to explain. Okay,
sorry, so, thanks. Yeah.
So there's a duality. So there's two different ways that you can. So there's open strings and closed strings, and they have a duality between them. And then if you take this low energy limit, which I just mentioned, the open strings, they will give you the quantum field theory, and the closed strings will give you the gravity theory. Okay, so that's the idea. But it's an excellent question, because this is just exactly what I want to explain. Okay, excellent. So we will get there. The only thing I wanted to do before I really enter all the details. So now let me. Sorry, I wanted to quickly share something else which I discovered while I was. While I was preparing these lectures, and just to give you some more flavor about what the okay, so let me share again. Okay, so this is a paper that I found while I was preparing these lectures, and so this is by Dr. Lauren Greenspan, who's in New York, and this appeared just a few weeks ago. And I thought, so this is, I think she has a PhD in physics, but she's now working in history and philosophy of science. And so it was very interesting, because I'm a physicist, and she exactly describes my work in terms of from the perspective of a philosopher. And so just to give you a little more motivation now at the beginning is the following. And so she writes, so that's the abstract of her paper. And I just wanted to read this quickly to you and make some comments from my perspective as being a physicist, just to give you some of the ideas that I would like to discuss later on. So she writes, I'm quoting this paper. Okay, so as the archive number, you can see the archive number here. So it's pretty recent. So based on string theory's framework, the gauge gravity duality, also known as holography. So I'm going also to explain why it's called holography. Has the ability, I hope you can read this, okay, has the ability to solve practical problems in low energy physical systems like metals and fluids. Okay, so, I mean, the word duality will appear in many contexts here. So, and one duality is that on one hand side, we have these very fundamental questions like quantum gravity and, you know, the theory of everything and so on. But on the other hand, there's also this very applied side to gauge gravity duality, where you can study metals and fluids. Okay, so this is very applied. And so in this paper, she is actually talking about this more applied side, but this is also what my research focuses on quite a bit. So I can say a little bit about this. Okay, holographic applications open a path for conversation and collaboration between the theory-driven high energy culture of string theory and fields like nuclear and condensed matter physics, which in contrast placed great emphasis on the empirical evidence that experiment provides. Yeah, so let me comment from my own experience. Yeah, so this is exactly true. So, and it's actually the fun of this field. that on the one hand side, I'm a string theorist. I work on this very fundamental aspects of theory of everything and so on. But now I have a lot of interaction with people working in nuclear and condensed matter physics, especially here in Würzburg. There's a big community in condensed matter physics. And now actually we have projects together with people from these very different cultures. And this is actually a lot of fun. And at the beginning, it's a lot of work to get, the framework to actually able to talk to each other. But it's been very fruitful and successful. And I would like to show you a little bit about this also in this talk, okay? So on one side, we have this theory-driven high energy culture, and then there's the other people who place great emphasis on the empirical evidence, okay? So, and now we're combining these things together, and it's really exciting, okay? So this paper, by Dr. Greenspan, takes a look at holography's history from its roots in string theory to its present-day applications that are challenging the cultural identity of the field. Okay, so there's a lot of things going on. So Dr. Greenspan writes in her paper, I will focus on two of these applications, holographic QCD and holographic superconductivity. And these are examples, but I can provide you many more examples. I will provide some more examples in this talk, okay? Highlighting some of the often incompatible historical influences, motives, and epistemic values at play, as well as the subcultural shifts that help the collaborations work. Okay, so I will give you some hands-on experience as being a physicist of these subcultural shifts, okay. The extent to which holographic research, arguably string theory's most successful and prolific area, I'm very flattered to hear this, of course, okay, must change its subcultural identity in order to function in fields outside of string theory, reflects its changing nature and the uncertain future of the field. Okay, here I'm not quite sure what is meant by uncertain future of the field. I mean, we have tons of things to do. I think I'm very busy and I'm not sure, I hope my future is not uncertain. And okay, maybe I can discuss this a little bit as we go along and look at the examples. Okay, does string theory lose its identity in the low energy application that holography provides? So if this is a question, and my answer is no, okay? And it's very interesting to see that on one hand side, we still have this, as was said here, this high energy driven fundamental physics, which is still very much at heart of the whole scenario. But on the other hand, now we talk to our colleagues who look at experiments. And but okay, so if this is a question, my answer to this question is no, okay. And these are all things I want to explain. I just want to use this as give you some motivation for the lecture. Okay. Does holography still belong under string theory's umbrella, or is it destined to form new subcultures with each of its fields of application? And wait, okay, so I already just mentioned this on my own slide a little bit. I think holography does still belong under string theory's umbrella, and it's this two-sided story of being both very fundamental and very applied. So my answer to this question would be yes, okay. And the new subcultures, I would still say, I mean, of course we collaborate a lot with our people, colleagues in condensed matter physics, but I mean, it's not really to the stage yet that we form a subculture with them. I mean, it's still that they view us as these high energy experts who are, quite distinct from them. So, I mean, this is a bit, I think, a bit early, at least from my experience, okay. So, but Dr. Greenspan writes, I find that the answers to these questions are dynamic, interconnected, highly dependent on string theory's relationship with its field of application. Okay, we will see this. In some cases, holography can maintain the goals and values it's inherited from string theory. I would be more strong, I would say, in all cases, okay, and let me give you some examples. In others, instead, yeah? Question? Was there a question? Okay, I'm not sure. Just interrupt me if you have a question. It instead adopts the goals and values of the field in which it is applied. Okay, let's discuss this using the examples that I will show to you. And these examples highlight a growing need for the STS community to expand its treatment of string theory regarding its relationship with empiricism and role as a theory of quantum gravity. Well, okay, I guess that's why you invited me to this school, okay? And I will hopefully give you some input that you can use then to address these issues. Okay, so let me go back to my slides now. I just thought that was very interesting that this is a topic which is being discussed obviously in the literature right now. And I think this is a very nice paper. And, you know, being a physicist, I think I can give you a lot of examples and insight in this tension between these very formal and these more applied aspects of gauge gravity duality. All right, let me go back to my slides. Let me try to go full screen again. So can you see my mouse moving? Okay, good. All right. Okay. Okay, so given this introduction, I hope you see that, what I want to show to you in this lecture is to find further examples of this gauge gravity duality beyond the original ADS-CFT correspondence, which was very firmly rooted in string theory. And then address this question in red here, is the original example arises from string theory, but is the duality valid more generally? I hope I can say a little bit about this, although of course this is an unanswered question so far. Okay, and I will show you these applications that were mentioned in this paper that I showed to you about calculating observables in strongly coupled QFTs, quantum field theories from the gravity dual. Okay, and before we enter the detail, let me stress again, I mean, so far there's no mathematical proof of gauge gravity duality, so it's still at the level of a conjecture, but it's an extremely useful conjecture, and I will also explain why it is so hard to actually prove this duality. Good, okay, so let me give you some oversight of what I'm going to talk about. So, okay, so as I already mentioned, there's 2 points which I have to address. One is the foundations of gauge gravity duality, and the other one is applications. And so I'm going to explain to you the origin of gauge gravity duality using this example of the ADS-CFT correspondence, which was proposed by Maldacena in 1997. Which is the best understood example and firmly rooted in string theory. And I will also explain how to test this duality. And then on the other hand, I will show you some applications, both to QCD or high energy physics theories, but also to condensed matter physics. That's what I've been working on mostly recently. So I can give you many examples here. Okay, so but here you see the outline, and let me start with the foundations. Also, one other point I should mention is that I realized that many other of the lecturers at the school, they will mention this relation between geometry, entanglement, quantum information, and gravity, which is also extremely topical. And I will also, and a very recent development, and I will also mention some examples regarding this as we go along. Okay, because that's certainly also very important in this context that I'm addressing here. Okay, now I'm going to start. Okay, and so thanks for asking this question. Where are the strings in the picture? So that's where I want to reach today. I mean, in the first hour even, and explain to you how does string theory generate this duality. Okay, so the most important word, of course, in gauge gravity duality is this word duality. And is there any question? I think people, no? Okay, good. So a duality, so let me try to give you a definition, a kind of very general, practical working definition of what I mean by a duality. And of course, this word has lots of meanings, and many of them will actually show up in the context here. Okay. So here, I just want to say that a duality means that a physical theory has two equivalent formulations, in the sense that, okay, so essentially I have two different Lagrangians or Hamiltonians. So I suppose everybody knows what a Lagrangian Hamiltonian is. Okay, sorry if this is a very basic question to you. I just want, I mean, please interrupt me if I'm using words that you don't know. Okay, but I guess Lagrangian is familiar to everybody. So what's a physical theory to us? It's a Lagrangian made of some particular fields. Okay, and then if this physical theory has two equivalent formulations in terms of two different Lagrangians made out of different degrees of freedom, different fields, but nevertheless, the dynamics is the same. And there's a one-to-one map between the states in these two formulations, then I would call this a duality. And okay, so I can make this even more pictorial. Okay, so imagine here you have some physical system, which you could even imagine of being a physical system in your lab. And then you have two physical theories. And so if a physicist says, I have a theory, it means that he or she has an action or Lagrangian or Hamiltonian made out of some degrees of freedom. And assuming that this theory describes this physics in this physical system, but then you have another theory or another Lagrangian that is made out of other degrees of freedom and describes the same physical system, then obviously there must be a relation between these two theories. And this relation, I would call a duality. Yeah. So this is a very, very general physics hands-on definition of what duality means. Okay. So it's a relation between two different Lagrangian that describe the same physical system. Now, coming back to this, I mean, you could now even imagine your physical system in a lab, something real, okay, in the world, okay. But today, so that comes back to the question that was asked earlier. The system will be so-called D-branes, okay, D-branes in string theory. And they will have these two different descriptions, and these two descriptions will be at the heart of this gauge-gravity duality. Okay. All right, so actually this general concept of a duality arises quite a lot in physics. And so there are some extremely well-known dualities, like the ones between the massive Thirring model and the Sine-Gordon theory. So this is a duality between bosons and fermions in 1+1 dimensions. But that's a duality where you have two quantum field theories. And that's a super well understood duality where you can actually write down the map that maps this one theory to the other one. But there's no gravity in this simple example. So the Sine-Gordon massive Thirring duality, it's called. But so the very special thing about this gauge gravity duality is that it's the only example so far known, okay, where on one hand side you have a gauge theory, which is a quantum field theory and which has no gravity. But that's actually dual in the sense that I show in this diagram to a gravity theory in higher dimensions. Okay, there's a question. Okay, very good. Let me look at the chat. You can't see the slides moving. Oh, that's bad. Okay, yes. Okay, so then you haven't seen my slides, then obviously it's pretty meaningless what I'm saying. Okay, let me try to share again. Sorry about this. Thanks for pointing this out. Can you see them moving now? Okay. Can you now see the slides moving?
Now we can see.
Okay, I'm really, really sorry. Okay, then it was pretty pointless what I was doing. Okay, let me backtrack then a little bit. Okay, sorry about this. Okay, so this you still saw, okay? And did you see this diagram at all? No, okay, sorry. No, I have to redo this because otherwise you have no idea what I'm talking about. Okay, so did everybody see this slide?
Yes, that one was already.
I wouldn't so. Okay, good. Sorry. Okay, then let me recapitulate what I said because it's pretty meaningless without the diagram. I was talking about the diagram. Okay, so I said a duality is a physics definition of the word duality, means that a physical theory has two equivalent formulations which have the same dynamics, and there's a one-to-one map between states. okay? And so this is the important diagram that I was talking about for the last 5 minutes, okay? So I was saying that you have one theory made out of a Lagrangian or Hamiltonian, and that describes some physical system, and then you have another theory with a different Lagrangian action or Hamiltonian made out of different degrees of freedom, but this theory also describes the same physical system. So if this theory describes the physical system and that physical theory describes that system, there must be a relation between them, and that's what I call a duality, okay? All right, sorry, I mean, okay, this is the diagram I was talking about before. Okay, so then, as I said, gauge gravity duality is this very special duality where you have a duality in this very general, broad physics sense, okay, where we have a theory which is a gauge theory that is a quantum field theory without gravity, and that's dual in this sense that I've drawn here to a gravity theory in higher dimensions, okay? So the gauge gravity duality, so I was mentioning before, there's many dualities in physics, especially in quantum field theory and 1 + 1 dimensional quantum field theories. You can map 2 quantum field theories to each other, and there everything is absolutely well understood. The only issue being that there's no gravity, and gauge gravity duality, that's what the name says, is the only known example where you actually map a quantum field theory without gravity to a gravity theory in higher dimensions. Now, already at this stage, of course, that poses lots of questions about the nature of gravity, okay? So if I tell you that gravity is actually the same as a theory without gravity, then you start wondering if it's really fundamental. I mean, if you really push it to the end, which I'm not going to do, okay? But you might want to push this to the end and say, okay, if a gravity theory in high dimensions is equivalent to a quantum theory in lower dimensions, but without gravity, then is gravity fundamental, question mark. I mean, you might ask this, okay, but I'm not going to do it, but just mention this possibility. Is there a question? No? Okay. Okay, so here already at this level, you might ask, you know, if gravity is really something fundamental in nature. Well, okay, let's leave this as an open question. I would still say yes, but you know, given this relation, maybe this is not so obvious anymore. Okay, I hope you can see the next slide. Okay, so as I mentioned, so gauge gravity duality is a conjecture which follows from a low energy limit of string theory. I mentioned this since somebody asked towards the beginning. So, so this is still a conjecture. And so now there's the word duality also appears in a slightly different sense. So remember this, so, I mean, this is something you have to remember for all of my lectures, that when I say duality, I mean a relation between two theories written in terms of different Lagrangians that describe the same physics. But there's another meaning of the word duality, which means that one key issue here is that a quantum field theory at strong coupling, okay, is mapped to a theory of gravitation at weak coupling. So that's a strong-weak duality, which also appears a lot in physics. And I will explain like a little more what I mean by quantum field theory at strong coupling, okay? But let me just point out that another meaning of the word duality in physics is that you go from a coupling and then go to another theory where the coupling is 1 over the original coupling. So this means a very big coupling becomes a very small coupling, okay? And that's interesting because at weak coupling, there's some very standard techniques for doing calculations, whereas theories at strong coupling, they're extremely hard to solve. So this is also something useful just from a calculational point of view, because essentially it means that you can map unsolvable problems to solvable problems, which sounds too good to be true, okay? I mean, if it were so easy that you can map all unsolvable problems to solvable problems, then physicists would be very happy, but there are some catches. I mean, the problem is that it doesn't work for any theory that you just pick. It only works for particular examples. And one difficulty is to find those examples where this makes sense, okay? Okay, then another word which is very important, which also was mentioned in this paper that I mentioned to you earlier, is the word holography. Okay, so, and this relates to a hologram, which I showed here. Okay, so what is a hologram? This is something where there's an information in a volume, say in 3 dimensions, which is stored in a 2-dimensional surface. Okay, so you have a volume with a surface surrounding it, and the same amount of information is inside the volume and at its surface. That's called the holographic principle, and there's many situations in physics where this actually happens, and certainly this is one of them. And in fact, what happens is that the quantum field theory in this duality is in d dimensions, but its dual gravitational theory is in d+1 dimensions. Okay, and so you can imagine that your quantum field theory sits at the boundary of this volume in which the gravitational theory is defined. And so that goes under the name of holography, because we store the same information in this d-dimensional surface as in the d+1 dimensional volume. So both the information content of the two is the same, but also the number of degrees of freedom. So I guess you know that physicists like to talk about degrees of freedom, and degrees of freedom is the number of variables you have in a given problem. Okay, so for instance, if you just look at a pendulum and you just have one point mass which goes on this, is constrained to run on the circle because it hangs on the pendulum, then the only degree of freedom that you have is the angle, which tells you the angle phi, which tells you the deviation from being perpendicular. So that would be a problem with just having 1 degree of freedom. Now, obviously, in quantum field theory, one problem of quantum field theories is that they have an infinite amount of degrees of freedom. But the point is that the number of degrees of freedom per volume here in this gravitational theory scales actually with the boundary, so with the surface in 1 dimension less. And so per volume, the number of degrees of freedom here is the same as in an area element at the boundary. Okay. So that's very important to understand this as well. And I will give more explanations of this as we go along. Okay, are there any questions so far? Okay, so let me move on, but okay, so again, if everybody knows this already, just tell me, then I'm going to go much faster.
May I ask something?
Yeah, sure.
Okay, my question is very generic. When you say quantum field theory in the holography and also in duality, this quantum field theory is only a mathematical fact, or is something more connected with the standard model?
Okay, yeah, this is an excellent question. Yeah, thanks for asking, and I will give you more details about this. Okay, so the answer is that in the ADS-CFT correspondence, okay, good. Maybe let me, okay, then if possible, let me see if I can share my, can I share my laptop? I hope you will be able to, can I share the content? Yeah, so I'm sharing the screen, and now let me, so can you see my screen? Yeah, it says lecture 1 Urbino, yeah. Okay. Okay, so if I say, no, it's not writing, sorry. If I write quantum field, sorry, one. So can you see me writing here, quantum field theory? Okay.
Yes,
Okay.
yes, we can.
Okay, so a quantum field theory, normally you have a Lagrangian. No, it's not writing again. Sorry, why it started out nicely, but then I'm sorry. Okay. Okay, so then if you know the standard model, okay. So then you have a Lagrangian density, and okay, it starts with some gauge field. So this F mu is d mu a nu minus d nu a mu, and then you have some fermions, and there's the Higgs field. Okay, so all these things enter, and in the standard model you have this gauge group which is SU3 times SU2 times U1. Okay, so you have the strong, weak, and electromagnetic forces and so on. So okay, so these AMUs, they would versus be the gluons, okay, and then your fermions there, they have the quarks, and so on and so on. Okay, so if you talk about standard model, this is what you have in mind. Okay, so and these quarks and the gluons, they have been measured accelerators. So these are particles that really exist. Okay, so or I would say where the theory matches the experiment, and so if you go to CERN and do a measurement of some I don't know, quark decaying into gluons and so on, you can calculate the cross section, and this is something which is absolutely real in the physics sense. Now, if we go to the ADS-CFT correspondence, then we have here the field theory side is this thing which is called a conformal field theory. Okay, and so it's in 3+1 dimensions. So the standard model obviously is also in 3+1 dimensions because our real world is in 3+1 dimensions. We have space and time, okay? And but here the story is that again we have a Lagrangian, so we have a supersymmetric gauge theory. So we have a gauge theory, so there will also be fermions, but there will be so-called gauginos, and then there will be scalar fields with some kinetic term. Okay, so these are called gauginos. So these are the super partners of these gauge fields which are here, and here we have some scalar fields which are again super partners here. Okay, so it's a very symmetric quantum field theory. Okay, now my pen is again not writing. So, and the message is that formally, okay, this theory here looks very much the same as the standard model, but in this the most basic example of ADS-CFT, or the best understood correspondence, it is a theory with a lot more symmetry than the standard model. Okay. And in particular, this theory has so-called scale invariance. Okay, so what does it mean to have scale invariance? This means, so assume, you sit on some ball and there's some physical process happening here, and then you inflate this ball to get this big, but still the physics doesn't change. Okay, that's something which is extremely rare. Okay, so normally if you change the scales. So for instance, in the standard model, you have confinement and asymptotic freedom. This means if you go to very low energies, so for instance, if you have confinement, then you have a quark and you have an anti-quark, and there's some flux tube. And okay, so now these quarks cannot be free. If you start pulling on them, okay, then there will be an attractive force happening, and so this is the so-called confinement. So these quarks, you cannot see them individually in nature, but so confinement means that there is no scale invariance, because if you change the scale, then the physics changes. Okay. But in the ADS-CFT correspondence, there's the CFT is a very particular quantum field theory. So where we can write a Lagrangian just as I did before, so something like this, okay? But the fields which enter here are not seen in nature. Okay, it's just a mathematical construction. I mean, it's a valid quantum field theory in the sense it's a renormalizable quantum field theory. It's in 3+1 dimensions. It's well defined from the point of view of theoretical physics and so on. But it doesn't describe anything in nature. I mean, you can invent lots of quantum field theories, and not all of them are realized in some physical system.
Yes. May I say something?
Yes.
Understood perfectly. Then my question is, it's clear that conformal quantum field theory is something very mathematical, but perhaps is it possible to find in the correspondence something on the boundary that is more similar to standard model? That this is not a standard road of research?
Yes, exactly. That's an excellent question, because this is exactly what I want to say. So the original ADS-CFT correspondence so includes. This is, I mean, I'm just repeating your question, but this is exactly the research question that many people are working on. Okay, so the original ADS-CFT correspondence includes a conformal field theory, so conformal field theories are abbreviated by CFT, and so this is not. I mean, this is the name of the theory is NX24 SUN super Yang-Mills theory. No, my pen doesn't work anymore. Come on. What's happening? Sorry about this. I don't know. My iPad somehow. But I think I have this written somewhere. Okay, then if it doesn't work, let me go back to my slides, because I must have written this somewhere, because this is exactly the point. So the name of the series NX24 super Yang-Mills theory. So this is this very academical CFT. And then the question is, can we make this work also for, say, for the standard model? Yeah, that would be extremely useful. And the answer is, in some sense, yes, but not entirely. Okay, so and this is just the complicated thing that people would like to so okay, so this now it's writing again. So this is okay, so that's the name of this very academical. So it's super means it's a supersymmetric theory. There's a symmetry between fermions and bosons and so on. So, and now the question is, does the duality also work for theories, i.e. Lagrangians, that describe something in nature? So that's the question that you ask, yeah, and that's the question that many people ask, and that's actually the topic of a lot of research. And let me try to sketch. So the answer is complicated, okay? But I will give you some examples. I mean, so this is an entire area of research. Which also goes under this name of gauge gravity duality, okay? And so let me say, I mean, this is some of the things I will also explain later today. So one problem, so it is possible to make progress. So, and I will show you examples, but some features cannot be changed. And then, so for instance, for example, so in the original ADS-CFT correspondence, so I said there's this SUN gauge group. And as I will explain to you, this rank of the gauge group is something which has to be infinite. Okay, so there is a limit of taking this n to be infinite. Okay, and this limit cannot really be removed, because then you remove the entire feature, and that's actually one reason also why this correspondence is so hard to prove. Okay, because it's impossible to undo this limit. But of course, if you know the standard model, you know that QCD is an SU3 gauge theory. Okay, so obviously 3 is not infinite. So this means I can make statements about n being infinite, but the real word in QCD we have SU3. And then the big question is, you know, are the statements that I'm making still meaningful, although I know that I'm not in the same regime, that, you know, my limit is n to infinity and not n is equal to 3. Okay, so that's an example for one of these questions that people try to address. So it, you know, so the duality does not work directly for the standard model. Okay, but are there features of the standard model? So standard model, I abbreviate with SM, that we can still describe in a physical sense. Although we know that we have n going to infinity and not n is equal to 3. And that's the whole game of gauge gravity duality research. Okay, you have to find those corners of physics where you can still say something meaningful, although you know that you don't have exactly the Lagrangian that you need. Okay, and this is okay. So now you might say that sounds strange, but this is exactly what I would like to explain also in these lectures. You know, that it still makes sense to, you know, you can still extract information, although you know that your Lagrangian is not exactly the one that's realized in nature. Okay, and that's the whole art, and that's why this is an art in physics and not mathematics. Okay, because we know that we work with something which is not realized, but still it can be useful. And so this is the research question. Of gauge gravity duality. Find examples where this is meaningful. Okay, and I will show you examples where this actually makes sense. Okay, so this is one message I would like to convey in the lectures. Okay, does this answer your question?
Yes, yes, thank you very much.
Okay, good. Then let me stop this again. Okay, let me go back to the go back to the slides. Okay, so now I need to share them again and to make sure that. Okay, no, it's again, this sharing is paused, so why doesn't that work? Okay, now you can see my slides moving, yeah, okay.
Yes, yes.
Okay, good. All right, so we were here. Okay, so I should be more precise in saying there are particular quantum field theories in D dimensions where this works, okay? And so it's not an entire art, or the research question is to find, you know, if you have a given physical problem, does the theory for this work, for which this works, does still sufficiently describe your physical problem? Okay, okay, I will give you examples, and then I hope this will become a lot more clear. Good. So that was the story about the hologram and the different dimensions that are involved. Okay, so that will also, this is also a recurring theme of these lectures that will come back. Okay, I will come to this question that we just discussed, that you just asked in detail very soon, but let me just take a little detour to this holography. So as in a hologram, the same amount of information, the same amount of degrees of freedom is stored once in the volume and once in the surface. And okay, so that refers to the so-called holographic principle, which has been around already for a long time, even before ADS-CFT, this was already around, okay? So this holographic principle states that the information of a theory in a given volume is entirely stored in the boundary surface of that volume. And this principle is inspired by the Bekenstein-Hawking black hole entropy formula that you see here. So where the entropy of a black hole is proportional to the area of the black hole divided by 4 times Newton's constant, okay? So really the entropy of the black hole is given by the area of its surface, okay, at the Schwarzschild horizon. And so because this is peculiar, because normally entropy scales with the volume in physics. And here in this case, it scales with the area. And that leads to this holographic principle. And so that seems to be a rather generic feature in quantum gravity that will come more, that we will encounter many times. Okay, so I like this example because it's actually very simple to Plato's cave. So just to make a connection to philosophy and something which probably everybody here knows, okay. So this holographic principle is a little bit like Plato's cave, okay. So if you remember, there's these prisoners that look at this wall and they see all these shadows. And then some other people, they carry around here a cat and a table and there's a light here at the back. And so the real objects, they are all 3-dimensional, but these poor prisoners, they are forced to look in this direction and they only see these shadows, these 2-dimensional objects. And holography is a bit the same, okay? So from the boundary point of view, we see these 2-dimensional objects, but in principle, the entire information is stored in these 3-dimensional objects, and there's a relation between the two, okay? Okay, so that was just a side remark to make connection to something which you surely know, okay? And so now let me enter more details of this about the physics, okay? So let me start at the very beginning, okay? So I'm a physicist, so from what is physics? So physics is the science of matter and its interactions. So on one hand side, you have some kind of particles in some general sense, and these particles, they interact with each other. Okay, so and this can happen in a lot of scenarios and circumstances, and we want to understand how they do. Okay, And so now let's come back to what I said at the very, okay, I've already been talking for 1 hour, but let me just go for another 10 minutes and maybe then we have a short break, okay? So, let me come back to what I said at the very beginning. So there's actually 2 different approaches. One is the one which I would call the kind of fundamental approach. Okay, so this is the question of string theory, for instance. So the idea is to find a unified theory of all the known interactions. So we say physics is the science of matter and its interactions. And now we want to find a unified theory of all known interactions. So on the standard model, we have electromagnetism, the weak and the strong force, and they can be quantized. And as you all know, there's this big challenge of unifying them with gravity, but then there's a challenge because this means we have to quantize gravity, such that all of these can be described in a unified scenario, this theory of everything, if you want, okay? But then on the other side, there's something which I would like to call the applied approach. Okay, so that's if you have condensed matter physics or nuclear physics and particle physics. So there, again, having in mind that physics is the science of matter and its interactions, we want to describe observables and processes in systems with a given interaction. And there's also a challenge there in physics, which is not quite as big maybe as this challenge of quantizing gravity, but still there's a challenge. And the challenge is that sometimes interactions can be strongly coupled. Okay, I will explain what I mean by strongly coupled in a minute, but this means that calculations become hard to do. So one example is Young-Mills theory that you see here. And so if you go to very low energies, then particles get very strongly coupled, and so the calculations become complicated to do. And oops, I was going in the wrong direction. So so then people in these more applied areas of physics, they fight. I mean, there are many issues, but one issue is to describe these strongly coupled systems. And so they appear in particle physics, nuclear physics, but also in condensed matter physics. And so here are some examples in condensed matter physics, like strongly correlated electron systems, high-C superconductors, heavy fermions, and so-called viral semimetals. And so there's a need of having techniques for dealing with the strong coupling. Okay, so what is strong coupling? So let me just explain this using this picture. So weak coupling means that we have some, okay, so physics is the science of particles and their interactions. So assume we have some particles, and then we want to describe the physics of this particle interacting with those particles. Now, if the coupling is weak, then we can decompose this problem, okay, and look individually how this red particle interacts with this blue particle and that blue particle and that blue particle and that blue particle. And so we can have a series expansion and decompose everything in this kind of 2 particle interactions, okay? And this means if we have some observable, we can perform a power series expansion that looks like this, okay? And so that's called weak coupling. And there's a well-defined procedure to deal with this, and this is called perturbation theory. Because you can treat the interaction as being a perturbation about the free or classical background. Now, if you have a strongly coupled system, this means that all the particles, they have these kind of springs between them. Okay, this means if you wiggle one particle, all the other particles are also going to wiggle, especially if you want to describe the physics of that particle. And you move this particle around, it means that all the others are going to move in a kind of collective motion. Okay, and then it means that this coupling constant will be bigger than 1, and then this power series expansion is no longer possible. And this means you cannot somehow decompose the interaction or the physics of this particle into interactions with the individual particles. You have to have the whole motion of the collective system at once. And that's a very hard problem in physics, and there's no known technique to solve this. So this is a totally well understood problem. It's like QCD at high energies, you do perturbation theory, you get precisions to 5 digits, and it's an absolutely well understood problem. But this thing is very complicated, and there's no generally accepted technique how to do this in general. So it's very welcome to have new techniques for explaining such physical systems. Okay, and now, so the message I want to convey now in the lectures is, okay, I gave you this fundamental approach of finding a quantum theory of gravity, and then this applied approach of solving strongly coupled problems in say, condensed matter physics. And now gauge gravity duality relates these two questions to each other. Okay, so and so these two approaches, they are much more closely related than we first thought. So this question of finding a unified theory of gravity on one hand side, if you solve that, it gives you also new tools for solving these strongly coupled problems in other areas of physics. Okay. Okay, and this I want to explain in more detail. Okay, and so the idea is first to explain the ADS-CFT correspondence, where we talk about this rather abstract theory, but where everything is understood. Okay, or most of the things are understood. And then we will ask the question that you asked a little earlier: can we also do this for realistic physical systems? Okay, so this is the plan. Okay, I think it's a very good point to have a 5-minute break, unless somebody has a question right now. Okay, can you see it now? Can you see it moving?
Yes, we can.
Okay, good. All right, so this is where I stopped. So I said the fundamental and the applied approach that I introduced are much more closely related than we thought. So this question for a theory of quantum gravity is related to this question of describing strongly interacting or strongly coupled particles. Okay, and so the idea is then really to map a strongly coupled quantum field theory. So for instance, QCD at low energies is such an example. Map this to a classical theory of gravitation. So this means we map the physics that happens in an event at the RIXS accelerator, for instance, or also at CERN, for instance. And there's a quark-gluon plasma of strongly coupled particles. And some aspects of its physics can be described by doing calculations for gravity in a black hole geometry. Okay, so, but I mean, the real physics is here. I mean, this is now, if you want a mathematical tool to describe the physics here. Okay, I mean, because one aspect is also that we look at gravity theories with a negative cosmological constant, okay, and they're not real, and they don't exist in the real world. But nevertheless, so it's really the idea that some aspects of QCD at low energies, where we have the strongly coupled system, regardless of this fact that not every entire aspect of our theory is exactly what we need, because we don't have this large n, so we have to take this large n limit, which is not there in QCD. Nevertheless, we can describe some physics that's happening here by this gravity theory. Okay, and I want to show you how also. So there's a very practical significance of the duality. So I can map a strongly coupled quantum field theory and to a weakly coupled classical theory of gravitation that is then solvable. And so I can do some calculations that I wasn't able to do in the original quantum field theory. Okay, and the most prominent example for this is the so-called calculation of the so-called shear viscosity over entropy density. Okay, so this goes to back to a very famous paper by these authors in 2004. And so that's the first example where people used a variant of this gauge gravity duality to calculate a physical observable that then describes the physics of the quark-gluon plasma in this accelerator. So we really start with something which is inspired by string theory, and nevertheless, we can use it to describe something that you can measure in an experiment. Okay, so that's of course conceptually very interesting. Although of course the relation goes over some steps. Okay, it's not a direct verification of string theory in a lab, but nevertheless there's a relation between some measurement and string theory, which goes over this gauge gravity duality. Okay, so let me just briefly explain what this is. So the shear viscosity is, so assuming you have some fluid between two plates, and then you move one of the plates with some velocity, and then there's a gradient in the velocity here. So because the fluid has a viscosity, okay, so it's like honey, or so there's some friction happening here. And this means the velocity becomes smaller if you go further into this fluid. And the strength of this gradient is the so-called shear viscosity. Now, you can form a so-called universal ratio, okay? So this keyword of universality is something which is very important in this entire business of using gauge gravity duality to describe real experiments. Because so universality in physics means that there are some macroscopic phenomena which don't depend on the microscopic degrees of freedom. And that doesn't happen very often, but there's occasions where this happens. And in particular, this is one particularly beautiful example where this happens. So, and as these authors found, so if you calculate the ratio between this shear viscosity coefficient and the entropy density, then gauge gravity duality, which is the strong coupling calculation using gravity, gives you this results, and it doesn't depend on any of the parameters of the theory. And so that's the key. If you have this universality, then if your physics doesn't depend on the microscopic degrees of freedom, then although we don't work exactly with the Lagrangian of QCD, we can still make a meaningful statements about the physics that's happening. And in particular, so it's more important to talk about this very strongly coupled theory rather than talking about the QCD Lagrangian itself. And ADS-CFT gives this ratio. There's H bar and K Boltzmann, so two natural constants. And there's a factor here of 1/4 pi. So, and that's a rather small number. Okay. So this gravity calculation, the calculation is performed with the Lagrangian describing this scenario, gives me a result for the physics that's happening here. Okay. And so due to the universality, I mean, there's the only physics information really is the size of this coefficient. And there's no dependence on the precise model that I'm looking at. And that's called universality. And now, astonishingly, if a measurement of this shear viscosity over entropy density is performed in this accelerator here, they actually confirm this result. Okay, as always, there's some grain of salt and so on and so on. There's, we have to, there's, some amount of debate, but essentially you can say that this is actually a number that has been measured in this accelerator. Okay. And that's, of course, a huge success for these string-inspired models. And the nice thing is because it doesn't depend on the details of the model, it actually has been measured in very different scenarios in the quark-gluon plasma, which is in nuclear physics, for cold atoms, and also more recently now even in condensed matter or solid state physics. Okay, so because this doesn't depend on the parameters of the theory or the Lagrangian of the theory, this universal ratio appears in many different contexts, and it was predicted by this gauge gravity duality calculation. Okay, so that's a very nice motivation to look for other examples of this type. Okay, before I move on, are there any questions about this slide?
Yeah, if I may, just
sure.
a comment on this universality that you're speaking about, because what I keep thinking of basically this the ontological commitments of this sense of dualities that we've seen in these lectures.
Yeah.
So my intuition is that basically the duality should somehow preserve basically something, and that something is what basically we should give some ontological meaning. So I think that what you are basically referring to as universality is precisely that. I think that that captures the idea, because otherwise it would seem puzzling. I mean, to basically have this ratio that basically goes across the disparate system like quark-gluon plasma and cold atoms, and of course in many advanced examples. So so I mean, I think that in these dualities and between one thing, QFT, and in classical theory of gravity, on the other hand, I mean, if we are to commit ourselves to some structure, I mean, that structure be preserved under that duality mapping. And I think that this is what the universality is basically capturing. Am I right?
Yes, exactly. I mean, that's entirely right. And it's due to the fact that this is a quantity which does not depend on the precise details of the theory. So if the synthesis ratio does not depend on the individual fields in the Lagrangian, then it can be captured by different models like the field theory and the gravity theory, as you just mentioned. Yeah, exactly. So so you have to have universal quantities, and then your duality has a chance of working for this example. Okay, so I think that's the order of things. I mean,
because otherwise, without this universality, I mean, this would, perhaps one should argue that it's just mathematical devices or basically representational in terms of, it's hard to basically accord them some physical reality if that universality wasn't there.
Yeah, I absolutely agree with you. Yeah, you're absolutely right. I definitely agree with this because, yeah, exactly. So, if you cannot test the duality, then it's not meaningful to have it at all. Okay, and these universal quantities, they provide a very nice test of the duality. Yeah, so that's the way I would put it. But yeah, I totally agree with you what you say. Yeah, excellent.
Okay.
Okay. Okay, that was on physics remark. Maybe I shouldn't. Okay, so what I just wanted to say is, okay, so this is this is the first example that was found now already some time ago, almost 20 years ago, and so there was a lot of interest in this result, and so some of the work that I'm going to show later on is something I've worked on myself, is to find other examples of concepts in low energy quantum chromodynamics, for instance, chiral symmetry breaking and mesons. And these provide other examples of quantities that you can compare in the QCD theory and also these gravity models. And I will come to those later. Just to say that this is a particular beautiful example of such a universal quantity, but there are others, and I will show to them. I will show them to you later. Okay, so this is a moment maybe to advertise my book, which it was already mentioned, so I guess you're all familiar with that. And okay, so maybe let me just point to the fact it's called Foundations and Applications. So maybe to just explain briefly, if you have had a look at this book, so it comes in 3 parts. Okay, so it starts with those concepts of physics that you need to know to understand duality. So there's quantum field theory, gravity, string theory, symmetries, and then the middle part is explaining the duality itself in terms of this very general relation to string theory. Okay, and then it has a third part where we talk about these applications, like the one I just showed on the previous slide. So the structure of the book is rather similar to this argument I was giving here, that on one hand side we have a connection to string theory, but then we have also applications to other areas of physics. Okay, so I should say Martin Ammon was my PhD student, well, a long time ago. And now he's a professor in Jena, which is another nice university town in Germany. Okay, good. Now, okay, so I gave you some examples of applications. But now let's go to this question that was asked at the very beginning. Okay, so where are the strings? Okay, and so this is where we are heading towards now, because I want to explain to you very generally what the concepts of this duality are. Okay, and I want to explain what the relation to quantum gravity, string theory, and so on is. Okay, so it's called the ADS-CFT correspondence, where ADS means anti-de Sitter space and CFT means conformal field theory. Okay, and that's the example where the duality was found, although in that case, it's a very abstract duality between two abstract mathematical concepts, which are two different Lagrangians. Okay, and but I mean, this is one thing in physics that, you know, the more symmetries you have, the easier it's to do calculations, but the less close you are to reality. That's always an issue in physics. There were some very beautiful toy models where you have a lot of symmetry and you can do beautiful calculations and everything is super nice. However, it has nothing to do with the real world. Okay, so that seems to be a general theme of physics. So let me explain this very beautiful, very well understood, very mathematically under control, very symmetric example first, which is the ADS-CFT correspondence. And then later we will go to these BH gravity dualities that we can apply to the real world. And then we have to have a, you know, we have to get our hands dirty and get rid of some of the beauty. But okay, the beautiful things are always the easiest to explain. And that's why I concentrate on this for now, and also because it has a relation to string theory, which you're probably also interested in. Okay. Okay, what is an anti-de Sitter space? Okay, so here you see a picture of an anti-de Sitter space, which is due to Escher. Okay. And so what an anti-de Sitter space is a space of constant negative curvature that has a boundary. So the boundary is very important for our holography that I already mentioned. Okay. So this is the metric of the space. So this is a Minkowski metric, and then we get an extra dimension, which is this holographic dimension. And then here we have an extra factor, which again involves this coordinate, which is here at the back. Okay, and L is the so-called ADS radius. Okay, so in this space, because it's constant negative curvature, it has a negative cosmological constant. And you know, there's some other ways of plotting this where this looks like a hyperbola, hyperboloid. And so, of course, our universe is not an anti-de Sitter space. Okay, so our universe is a de Sitter space, and it means that the metric looks slightly different. Okay, so in some sense, this is just a mathematical construction, but it has some very beautiful mathematical properties. Okay. Oops. So now if you wonder what these angels and devils are, okay, so these are drawn there by Escher, because if you project, so the anti-de Sitter space looks like a can or a tin or a cylinder, which goes all the way to infinity. But one direction is time here. So if we cut at a constant moment in time, that's what you see. And the point is that these angels and devils, they all have the same area, but in this projection, they look being more close to each other at the boundary than in the middle. Okay, so you are probably familiar with the Mercator projection of a sphere. Okay, so if you have a globe, a picture of our world, okay, so the Earth. And then if you want to draw this on a map, which you can put on your desk, you have to use the so-called Mercator projection. And this means the Greenland and the Antarctica on your map, they look much bigger than they are in nature. Okay, so the things which are close to the equator, they look much smaller on the map of the world than Antarctica and Greenland in the North Pole. Okay, and that's an effect of a positive curvature. So our Earth is positively curved. Okay, it's a sphere. But here this hyperboloid is negatively curved, and this means the things which are near the equator in the middle, they look much bigger than the things which are at the boundary. Okay, so it's the inverse of a positively curved object. Okay, so just to give you some intuition. So this is like a hyperboloid. And so this is the center of your anti-sitter space, but then actually, it's actually an infinite distance to go all the way to the boundary. Okay, so it's a non-compact space. So the distance from here to the boundary is infinite because you see these things get smaller and smaller and smaller. And well, I mean, in the infinite limit, you reach the boundary, but still this distance is infinitely long. Okay, so this is an anti-de Sitter space. And the reason we look at it's that the symmetries of this mathematical space are the same as the conformal field theory, this conformal symmetry in the conformal field theory. So this is our curved space in which we have gravity, and this conformal field theory, this will be defined on this blue boundary of the space. Okay. So now I explained what an anti-de Sitter space is in ADS, but now I also have to explain what a CFT is. So a conformal field theory, or CFT, is a particular quantum field theory. And it has, again, a lot of symmetry. Okay, so the fields transform covariantly under conformal symmetry transformations. So that's the mathematical term of saying this. And so what is a conformal coordinate transformation? Well, it's a transformation that locally preserves all the angles. Okay, so if you have a rotation, a translation, or a scale transformation where you blow up things, then locally the angles are the same. But nevertheless, this is a very strong symmetry, and actually there are very few examples in nature where we have the scale symmetry. I mean, this is a conformal symmetry. This is something rather rare, actually. But here in this particular quantum field theory, this happens. And if you have this huge amount of symmetry, then you can, I mean, the more symmetries you have, the easier your life gets, because then the calculations become a lot easier. Okay, so it's the more symmetric things are, the less parameters I need to describe my physical system. And so normally if I calculate the observables in the quantum field theory, so that, for instance, the so-called correlation functions, which are examples for observables, then in such a conformal field theory, they are determined up to a very small number of parameters. So in QCD, which is not conformally invariant, if I calculate the cross sections and so on, observables, I have to do a perturbative expansion and approximation, and it's all very cumbersome. But here, because I have so much symmetry, I can almost write down the results just based on the symmetry. Okay, and that's why people use this example. So it's not, this particular theory doesn't describe anything in nature, but it's very easily to calculate with, and it has a lot of symmetry. And now the interesting thing is that the symmetries in this field theory are the same as the symmetries of this anti-de Sitter space. So the symmetry groups, so physicists or theoretical physicists write symmetries in terms of mathematical groups. So a group is a mathematical structure that describes a symmetry. And the symmetries of an anti-de Sitter space in D+1 dimensions is the same as this symmetry group of this conformal field theory in 1 dimension less. Okay, and that's actually a key why this duality between the field theory and the gravity theory works, because we have this holographic principle which tells us that the number of degrees of freedom is the same in the two theories. And now I also tell you that the symmetries are very strong and they are the same in the two theories. Now, for a physicist, if you say I have two theories and they have the same amount of degrees of freedom and they have the same symmetry, then a physicist will always conclude that it means that this theory must be the same. Okay, of course, that's not a mathematical proof. Okay, mathematicians, they would be horrified by this statement, but okay, I'm a physicist, so I'm allowed to say this. So if I tell you I have two theories and they have the same amount of symmetry and they have the same amount of degrees of freedom, they just got to be the same. Okay, and so that's what the essence of this, why this duality works. Okay, But then now you can ask, is there any question about this? I mean, before I move on. Okay, I mean, does it make sense what I'm saying? Are you totally overwhelmed, or have you heard this before? For me, it's very hard to tell.
So can I ask this elementary question about symmetry? So, you know, you call it the gauge gravity duality.
Yeah.
And but I think in this discussion you were emphasizing the conformal symmetry, but the conformal symmetry is not a gauge symmetry.
Exactly.
So, but the gauge symmetry is also, it's important for there to be a gauge symmetry for the duality to hold.
Yes,
right?
Very good question. Excellent question, and I will describe this. Okay, so this theory is so symmetric, it has lots of different types of symmetries, okay? It has a gauge symmetry, which I will come to later, and there's this conformal symmetry, and it also has supersymmetry, okay? So now conformal symmetry and supersymmetry, they are examples of so-called global symmetries, whereas the gauge symmetry is an example of a so-called local symmetry, which means that the parameter depends on space and time, okay? And it's in fact these global symmetries that occur both in the field theory and the gravity theory, whereas the gauge symmetry of the quantum field theory you cannot directly see in the gravity theory. So these symmetries are treated on a different footing. Excellent question. So the gauge symmetry is distinct from this conformal symmetry. So this theory is a gauge theory, and on top of it is conformally invariant and supersymmetric. So these are three different symmetries, two of which are global and one is a local symmetry. And the statements I've been making here about the symmetry groups coinciding and so on, these are statements about the global symmetries. Okay, very good question. Okay, anything else? Okay, so yeah, go ahead.
Thanks, that was very helpful. And just to, you know, when you hear the name gauge gravity duality, you imagine that it's the gauge symmetry that's essential for a duality to hold. But what you said just now suggests that so I guess one way of asking my question is, do you imagine, are there dualities where the field theory does not have a gauge symmetry at all, but just has the conformal and the supersymmetry?
I think, wait. Okay, so in this restricted scenario that I'm talking about here in the context of the ADS-CFT correspondence, they are all gauge theories.
Okay.
But if you go more widely in the context of physics, I mean, there's other dualities, which I mentioned, this duality between the massive Thirring and the Sine-Gordon model, but that's not a duality involving gravity, but these theories are not gauge theories, like for instance. Okay, so, but it's an excellent question, and I will give you more details as we move along. Okay. So I will come back to this point. So just for now, I think you should remember that here I'm talking about the global symmetries, not the local symmetries. And where I will tell you what happens to this gauge degrees of freedom in a few slides. Okay. Good. But before I get there, I have to take a slight detour because, okay, you should say, at this stage, you should tell me, yeah, why should I believe this? Okay, you should say, okay, fine. You tell me I have two theories, one has gravity, the other doesn't. And you tell me they have the same amount of degrees of freedom and they have a lot of symmetry and the same symmetry. And I've been advocating now that they should be the same or they should be dual to each other, okay? But then you should still ask, but why on earth did you come up with this example, okay? It's still extremely non-trivial, okay? That I can do a quantum calculation in a flat space. And then on the other hand, can do a gravity classical calculation and get exactly the same result for some physical observables by doing a completely different calculation. That's actually what's happening. I will show you examples where you can do a quantum computation in a flat space on the one hand side, and you do a gravity calculation in curved space on the other side. And you get exactly the same result by doing two very complicated but very different computations. So, you know, how should anybody ever have thought about this? Okay, and the reason is string theory. without string theory, this would not have been found. Okay, so that's why I'm going to explain now a little bit about strings. I'm going to take a slight detour and explain a few things about string theory that we need to know. And then it will become much more obvious. And so coming back to the question that you asked at the very beginning, where are the strings? So this will be the answer now. So we need to know a few facts of string theory, because without string theory, nobody would ever have thought about these things. Okay, it would appear as a very strange coincidence, but it's actually a consequence of string theory. Okay, so that's why we need to talk about strings a little bit. Okay, so I'm taking a slight detour about string theory, but I'm just going to tell you those aspects of string theory that we need to understand gauge gravity duality and the ADS-CFT correspondence. Okay, so I guess you all have heard about string theory. So this was developed in the quest for a unified theory of fundamental interaction. So it provides a quantum theory of gravitation. Okay, you might discuss if it's the unique, the right and real one, but it does provide a quantum theory of gravitation. And it describes the standard model of elementary particles and gravity in a unified framework also. This we can certainly also say about string theory. And it leads to a reduction of the number of free parameters in the standard model. Okay. So string theory is really a candidate for providing all of these aspects. So the question is, how can we have a unified theory of gravitation and the standard model in a unified context? Well, we have to provide a quantum theory of gravitation, but okay, there's all these issues that if you quantize gravity in the standard way, it's not renormalizable, and then the theory doesn't make sense, and so on. But string theory, by the fact that the elementary particles are extended objects and not just point-like, so the locality is abundant at very short distances, then we naturally have a cutoff that makes all our integrals finite and ensures a finite regular quantum field theory. And this cutoff is provided by the length of the string. Okay, but these strings, so the length of the strings will be made out of universal constants, namely h bar, the Newton constant, and the velocity of light to the third power. So if you combine this in such a way, then you get something which is of the unit of a length, yeah. But it gives you this absolutely tiny length, okay, which is far beyond observation at any particle accelerator, okay. By 15 orders of magnitude, it's impossible to resolve at such small scales. But nevertheless, conceptually, it's very interesting that you have this length, which makes your theory finite. Okay, so direct experimental tests are not possible today. Okay, I mean, I think that's a very useful euphemistic statement. Of course, I mean, also, I think in the next 20, 30 years, it will not be possible to directly test this experimentally, because, I mean, this is really far off any particle accelerator that we can build. Okay, but the important point now in our context is that string theory actually provides the framework for gauge gravity duality. You can use string theory as a set of mathematical equations, which very naturally gives you this duality between gravity and quantum field theory. Okay, so let me tell you about a few features of string theory that we need. And so one feature is that on the one hand side, we have open strings. And on the other hand, we have closed strings. Okay, so open strings, so string really means the string of a violin or guitar or piano. Okay, so where the two endpoints, they are fixed somewhere, and then you have some vibrations, some fluctuations, which, you know, there's the lowest mode where the string just does this. Okay, so imagine you have a violin or guitar, and if you strike a very low tone, it does this. Okay, it doesn't have a lot of wiggle, it's just a small. And the small amount of wiggles is like a dipole moment, and that's why this corresponds to a gauge field, because it's a spin one object. So there's just this field A mu. Okay. So essentially these gauge degrees of freedom of the standard model that we were talking about, so the gauge symmetry, okay, that's associated to the open strings in string theory. Okay, and closed strings, they look like this, and then you can show, so no, unfortunately I can't show because my hand is in the plaster, okay. Do you know what a quadrupole is? So this is if you have your circle and it like vibrates like this, like that, like this, like that, okay. So this is a quadrupole moment. The quadrupole moment is a matrix with two indices, and that provides you with a graviton, okay. So the fluctuation modes, the lowest energy fluctuation modes of the string is a quadrupole moment, which corresponds to a metric. And metric gives you gravity theories, okay? And whereas the open strings, they give you gauge theories without the gravity. Okay, so essentially we just have two types of degrees of freedom, the open and the closed strings. And the open strings, they give us gauge fields, and the closed strings, they give us a metric, a graviton. Okay, good. I guess the break is coming up, so maybe should we take a break here, and I will continue there after the break.